Today's discussion topic is on CAT swarm optimization techniques. As the name suggests, this algorithm tries to mimic the cats. Yes, I am talking about the domestic cats. So, if you have ever observed your cats, cats mainly have two types of motion. One is tracing, another one is seeking. When the cat is seeking, he is actually observing, but he is not doing any work. So its velocity is zero. Change of motion, location is also zero. But at the time of tracing or tracking, the cat is trying to move towards its goal. Actually, what happens is when the cat is sitting in a specific place, and you can see that it will constantly observe multiple things of its interest. So, but if that interest is, if suddenly it sees some things of most importance which need instant attention, the cat moves up from its location and starts to chase or run towards that desired object with which the cat has some plan. So to be more precise and more simple, if a cat sees a food, or cat sees a bird, or cat sees a lizard, it will instantly move up and then try to catch it. So it instantly attains some velocity, and yes, its location changes at a rapid rate. So in this case also, we have tried to mimic, or rather the authors have tried to mimic this behavior of cat in identifying the optimal value of our objective function. Here also there will be a problem. Say for example, y is equal to x square. You have to maximize y, and so to maximize y you have to change x, no other way around. Now how we are trying to change these values of x? Suppose x can be in between 0 to 1, but not equals to 0 or equals to 1. So now how we are planning to change x? So in any type of bio-inspired optimization technique, it will give different process of generating new value of x. And this CAT swarm optimization technique is no different. This is of course the example of bio-inspired optimization technique, and it is a very well known technique. Its advantage is that it has two different procedures of attaining the optimality, and based on the logic, based on the requirement, CAT took a decision to opt for a certain procedure. Whether to go for tracing or whether to keep on seeking depends on the cat and what it is observing. So here also, in case of mathematical application of this CAT swarm optimization technique, the first step is to determine whether the location of the solution needs some change or not. If it needs some change, we go for tracing. If it doesn't need for any change, we go for C. Anyway, let us move towards the problem that we want to solve now. So here, as you see, I have already said, so in this problem we are minimizing. That means we want to identify the minimum value of y by changing the value of x within 0 to 1 but not equals to 0 to 1, and x must be a member of the real number set. But here our goal is minimization. But the first slide I was giving the example of maximization, the same problem. Anyway, this is the problem. Now how our main goal is to how I can generate new values of x with the help of cat swarm optimization technique. Now this is the schematics of the entire technique. So what is it? Cat swarm optimization technique. First is, let us randomly select n number of cats having n number of dimensions. What we want to say is that randomly select m number of solutions within your feasible domain of solutions. As you have already known that in optimization problem there is always something known as feasible domain and infeasible domain. In our case, they have said your x must be within 0 to 1, cannot be equals to 0, equals to 1. So for your case, this is the, I think, the region of feasibility. And so anything here or anything here, it is region of rejection. You cannot take values from those places. So taking m number of cats randomly means each cat is a solution. Each cat is a solution. Whether it is the selected solution, I don't know, but it is randomly we have selected this solution, which is the characteristic of meta-heuristic algorithm. In case of meta-heuristic algorithm, the first thing is to randomly select the solution such that the chance of getting into a local minima is minimum. So in case of classical optimization technique, what happened is we try to select the values of x from 0 to 1. We begin from 0, we finish at 1. But here that is not the case. You can randomly select any value in between 0 to 1, say for example 0.5, 0.1, 2, 0.7, as you wish. So now what is happened? This each cat has n number of dimensions. N number of dimension means these cats can move front, move back, move left, move right. It can run. So all these things are dimensions. Running ahead is one dimension. Running behind is another dimension. Running left is another. Running right is another. Walking ahead, walking behind, walking left, walking right. So in such a manner, n dimensions are allowed for this cat, for its movement. Although this n dimension thing is not very important, but mathematically we have to be correct. That is why I am mentioning this n. But the number of cats is m. So there are m number of cats who are allowed to move around in n dimensions. Now the thing is that based on the mixing ratio, now what is your mixing ratio? Mixing ratio is when you are saying that randomly select m number of cats. Now in this m number of cats, the cats which need to move or need to attain a specific velocity is also there. And the cats who does not need any velocity, they are also there. What happens is, numerically what we do is we randomly select few of the cats for motion, for velocity, for attaining velocity. And the remaining number of cats and the remaining number of solutions are kept at the same location. So that is why we say that in the second part of this algorithm, try to select the solution which are under the tracing mode or movement mode, which needs a velocity or which has been assigned a random velocity. So you see here it is written, cats with velocity are in tracing mode, cats without velocity is in seeking mode. So although in reality first seeking mode takes place and then the cat goes into tracing mode to attain its goal. But here what we do is we try to divide the solution into the tracking mode solution and seeking mode solution. Advantage is that straight away we concentrate on the region where the convergence can take place. Convergence means selection of the optimal location can take place. So that is why we try to filter out the cats or solution which can be in the seeking mode. That means its fitness value will not be in a good position, and few of the solutions will be in the tracing mode because of its probability, because of the probability of the solution to attain the optimality. But it all depends upon probability. That means it is everything is imaginary here. In reality, what we do is, suppose here I am saying M. So we select suppose 5 cats in tracking mode and remaining m minus 5 cat in seeking mode. Now you can say how we have selected it. I always select based on the fitness value, or I also select randomly. So this part I am coming later on, but the recent part will be the next part of that means the part 3 will be. Yes, you see you have filtered out the cats in the tracing mode. Now what you find? You have to find the velocity. Correct? Now in the first iteration, just like particle swarm optimization technique, this velocity is assigned randomly. So, and this velocity is also, that's why this location is already assigned randomly, because randomly selecting M means randomly selecting the location of the M number of cats. M number of cats means there is M number of location. M number of location means there are M number of X, KT. So what happens now? After adding these two random values, and random means, always remember, random function in case of bio-inspired optimization is always in between 0 to 1. That means it will never take the value of 0, it will never take the value of 1, but it will take the different values inside 0 to 1. but it may be, those values may be real number, not maybe, surely they will be the real numbers. Okay, so now that we have generated this x, we have find out the value of this x, we put it into this equation, and this equation will give you a value of velocity of the cat. K indicates the kth cat, D indicates the dimension. I have say n, so although this is 1 to n, but in between that there is 1 to d also. So d is another dimension also. D is less than n, but d is there. So because dimension means in some cases what happens, one cat may have 8 dimension, some other cats may have 10 dimension. It's example. So maximum there will be n dimension, but yes, d is also allowed if n is greater than d. Clear? Moreover, this d is actually, they are saying dth dimension. We say na dth. Then d is actually 2. That means the second dimension. This velocity is of the kth cat. If d is 2, that indicates that the second dimension. This velocity is for the second dimension. If d is equal to 2, if d is equal to 3, third dimension. D is equal to 4, fourth dimension. That way. So here you see that VKD, this is also random. This random will be selected, and this is random. These and these are actually same. So VKD, again the same value you have to give in VKD, not different random values. Then plus C1 into R1 into x base d minus xkd. So here this C is any constant, okay, but R is, you see here it is written, R is random number between 0 to 1, okay. So R means random value, just like this function, random function. Any value more than 0 to more than 0 less than 1, any value it can accept. And it will be allocated to him in a random mode. Now next you come to these two parts, x base d, xkd. Xkd is well understood what is xkd, right? Now here you remember this xkd is not same, but this xkd and this xkd is same. Okay, and now at the time of the first iteration, xkd will be equals to x base, correct? Because we have not yet evaluated whether this value of x is yielding the best results, correct? So here I have told a little bit mistake. I have done a little bit mistake. The mistake is that random velocity should be assigned to those cats who are selected under the tracing mode. So the velocity will be randomly assigned, yes. And C1 is constant, 1 or 2. R1 is random function, 0 to 1, any number. And now you come to the fact x base d minus xkd, right? So x base d will be the same as xkd. Okay, now I have again done a mistake. There I have been doing the mistakes. Actually what happened is, yes, randomly the location whatever I have said, it is okay. The thing is that these two equations will follow circular motion. Okay. Now what happens? It has determined the V of second iteration, correct? So this V will be put into here. This V will be put into here. This is second iteration. Earlier position X will be put it here. Earlier location. And a new location will be generated, or new X value will be generated. Can you getting my point? The first part will be you have been assigned a random location, having a random velocity. So this is random, this is random. You get another X. Sorry. Now you put this X here, and this X based, as is the first iteration, this X based will, there will be no X based, so there will be only this X at the first iteration, not in the other iteration. Because there is nothing called as X based, because this is the only single iteration. And R1 is your random numbers, any value in between 0 to 1. And C is your constant. Now, regarding C, I want to say that if you want to activate the iteration process or speed up the convergence process, then assume C to be higher value. And if you say, okay, let it converge at its own will, then you take value of C in a lower section. So generally we take C to be 1. Although it negates the impact of C, because 1 will have no impact, but for general cases we use this C is equal to 1. So now let me recap. Random V, random X, you get a X, you put it here in this X. Random R1, constant C1, VKT. From where you are getting this VKT? This is the same VKT, correct? That random velocity awarded to that point K. And you get a new V, correct? Now what happened? This is a new V. I say it follows a circular motion. Now what you do is, this new V you put here again in the second equation. This X is your old X, this one. So old X you put here, old X, you get a new X, correct? Now put this X into this equation to get a new V. And after the second iteration, there will be X based will also be there. Now what is X based? Now this is a very interesting thing to do, to explain. So for the first iteration I have got a X, take it as 1. And then again in the second iteration I have get X2. So, your problem is y is equal to x square. You have to minimize y. So, when I put x1 in this equation, we get y1, suppose. And if after putting x2 in this same equation, I will get a value of y2. So, if y2 is less than y1, then we are going towards our goal, because our goal is to minimize y. And so first iteration y is more than the second iteration y. So that is why x2 will be better than x1, because at x2 I am getting a minimum y, which is our desired goal. So then you place the value of x2 here and value of x1 here. Then randomly another value will be generated for R. C will be same one. V will be this V. and our new V will be there. Then again you take this new V towards this old V, take this X as X2, this one, X2, and you get a X3. And again you put this X3 into this Y is equal to X square, your objective equation. You get a Y3. Now you compare Y3 with Y1 and Y2. If Y3 is the minimum among Y1 and Y2, then X3 will be the best, X best. So in this way, these iterations will go on and on, until and unless our desired number of iterations get finished, or our desired goal of optimization is achieved. Okay, so that is why it is saying that, you see, if VKT is greater than Vmax, then of course VKT is Vmax, else VKT will be remain as VKT. Now you will say, what about seeking mode? Seeking mode I have not gone yet, correct? So the cats which are under the seeking mode, so there also there will be a selection probability. Which cats among them will be selected? And that will be selected based on the fitness value. So here the formula is very easy. Formula is AP, I think AP I minus APB divided by AP max minus AP min. Sorry. So API is the fitness value of I. Now this fitness value is nothing but this one. Correct. Whether you can, if you wish, you can easily use the value of Y for the value of X in case of the cats under seeking mode directly in this equation. That means API means the value of Y at the ith value of X. Sorry, I don't know whether you are getting my point or not. So what is happening here? We are calculating a PI, which is known as selection probability. And the value is, or the formula is API minus APB divided by AP mean minus AP max. And APB can be minimum when our goal is to minimize, or can be maximum when our goal is to maximize. Now you will say, what is this API? API is simply the fitness function. In this case, you can simply write the value of YI, because that is what is depicting the fitness of the new generations. Because the objective equation is Y is equal to X squared. So when I am generating a new value of X, I am putting into this equation. And if Y is more than the other Y, it is rejected. If Y is less than the other Y means the Y at the previous iteration, it is accepted. So you can straight away put the value of YI as our API. Now as our goal is to minimize, so you write here the Y minimum, and in the denominator you write Y max minus Y mean. So this way we will find the probability, selection probability of the those randomly selected cats which were not selected for tracing mode. So with the help of the selection probability, what we can do? With the help of this selection probability, what we can do is that we can arrange these values of cats which are not selected in the tracing mode but is present in the seeking mode in a sorted manner where the highest rank cat is the most selectable, or highest ranked cat has the highest probability of selection. So what we will do with the highest probability of selection? What we will do is, if this part is finished, that means along with the cats which we have selected as tracing, if we finish our iteration with them, we will move towards this one, seeking. And at that time we will select the top ranked or highest probability cat from the list of cats which are left out in the seeking mode. And this selection will come one by one until our desired number of iteration is finished. Okay, so this is more or less the trace. This is cat swarm optimization technique. It is very easy to solve technique. So the steps are very simple. Let me recapitulate it once. So before closing, I want to just recapitulate what we have done in cat swarm optimization technique. Here what we have done is, we have randomly select some cats, means some solution. Suppose this is your feasible place, or what we say as region of feasibility. We have selected, suppose 10 number of values from here. Let me say, this is example. And these are all random values of the design value. Here our problem was y is equal to x square, and I have to minimize y by changing x. X can be any value in between 0 to 1, but never be equals to 0 to 1. And there is another condition is that x must be a member of set of real numbers. That means it cannot be an imaginary number. So what I have done is that based on this constraint, I have got my feasibility place, and from there I have randomly selected 10. What is this 10 number of values? 10 different values of x in between 0 to 1. Now what I have done? The next step that I have done is that within this 10 number of values, I have selected, randomly selected 3 values for the tracing mode, and remaining 7 I have kept as reserve in seeking mode. I have already discussed that cat have 2 modes of action. One is tracing mode, where it tries to achieve some objective, and another one is seeking mode, where it constantly observes different opportunities it is having, and once it decides that this is my best opportunity at this current stage, it converts itself into the tracing mode. How it converts into its tracing mode? From seeking to tracing, velocity is added here. So what I do is, in case of numerically, while we are mimicking, we place 3 values in TM and 7 values in SM. That TM means tracing mode, SM means seeking mode. And with this 3 value, I put it into that equation. That equation is X new is X old or current, you can say, plus V old or current. Now this V is randomly selected and this X also randomly selected for the first iteration. Basically not randomly selected, within these 3 values of X under TM, one is given here. So it is yielding a new value of X. So that new value of X I put in the velocity equation, where V new is equals to, I think, V old plus C into R into X best minus X old. Sorry, not old, X new. So this X new is put it here. These are, I have already discussed, any value in between 0 to 1, random function. Any value in between 0 to 1 but not equals to 0, not equals to 1. And V old, you know, this is your V old. And you get a new V new. In the first iteration, there will be no X best. So X best is 0 for the first iteration. But from the remaining iteration, X best will come. Because when you compare X1 with X2, and if by putting X1 you get Y1 and putting X2 you get Y2, then if Y2 is greater than Y1, so X best will be this one, X1. And if Y1 is greater than Y2, if Y2 is greater than Y1, right, our goal is to minimize, correct? So Y1 is minimum compared to Y2. That means Y1 has been yielded for X1. So X1 is giving better result, correct? But if it is changes, then X1 will not be the best, X2 will be the best. So that way we have to work. So now that this one is there, so you are getting this V news, and now what will happen? You have got the V new, then you put this V new to as V old, X new to X old, then another new you will receive. Put this another X new to here, and then there will be random, there will be C will be anything between 1 to 2, I have already discussed. And this will be your V old, and you get again, you get a new V. So this way the circular motion will go on. So what is happening if you observe is, constantly you are getting a new value of X here, correct? And you will put these X's to Y, this equation, your objective equation, to get your new value of Y. And if your new value of Y is better than the previous value of Y, then the X best will change also. Okay? So that means you are constantly generating X with this entire method, tracing method. And now you are doing it for not only for the single value of X, you are doing it for the 3 number of values of X, but simultaneously. Okay, here I have shown the thing for the 1 value of X simultaneously there will be another value of x because I have selected 3 and another value of x. If from this 1, 2, 3 the optimal value has not been generated, then we goes to the seeking mode, where 7 number of values of x is already waiting. Now there what we do is we try to calculate the PI, selection probability, and there what we do is that 7 x's are arranged in as per their selection probability. And how we can find that selection probability? It is fitness value I, that means the current fitness value, minus, if it is minimization problem, then it will be the fitness value at minimized condition, and if it is a maximization problem, this will be the maximized value of AP divided by AP max and AP min. So there you get a probability. So more the probability, more is the selection potential, and that way 7 will be arranged. So once you are done with the 3, you will try to select the topmost value of this remaining 7. So in this way the iteration will go on until your desired accuracy has been received, or the desired number of iteration or allowable number of iteration has been reached. So now you can see that there is another algorithm known as particle swarm optimization, and you will say what is the difference or what is the benefit of using CAT's swarm optimization technique instead of particle swarm optimization technique. The main benefit is the rate of convergence, and you can modify this rate of convergence by modifying the C value. So this saves a lot of value for expended, which is otherwise expended due to optimization. So, and another thing is that you can also experiment CAT's swarm optimization technique, analyze its potential by applying to different topics of research. And in the previous slide I have shown some of them, but you can of course use other CAT's swarm optimization technique in other case studies also. Okay, so up to this, this is what I want to tell you regarding CAT's swarm optimization technique. This video is available in the YouTube, and I request you to subscribe to YouTube. Don't just watch and go by. So with this, I want to finish this short presentation.